All right, so we're going to look at log functions and what their graphs look like also. Yay. You're going to see that they look somewhat familiar, because if we take the log form of an exponential function, this is the exponential function we looked at yesterday, and this is its log form. How do you go from here to here? All we really did was drop the log and we switched the x and the y, didn't we? You take the same base, so this is log base a, obviously it's going to be some number, of some number, in this case y, equals another number x. So all you do is keep the same base, and in exponential form, isn't a the base? So the base doesn't change. What you're taking the log of and this number here do. So all we did was switch those two. So how are you going to convert log base 2 of 8 equals 3 into its exponential form? 2 to the third equals 8. Is that a true statement? So would you agree that it works? Yeah, and I will show you how to do this on your calculator. So right now I'm not going to prove to you that it works there. But we can also go backwards. So here's the exponential form. 3 squared equals 9. You agree that's true. So write it in its log form. Log base, same base, right? 3 of what? 9 equals 2. Good. What about this one? Log base 10 of 100 equals 2. That's not so hard, right? That's why that's why you have so much homework, because that's what several of those questions are. So that's nanoseconds, right? Can't they all be the same? All right, so then we have what's called a common log. So this last one that we had was a base 10. If you ever see it's written, this could be written as just log of 100 equals 2. So if the base is missing, in other words, this 10 here is missing, it's your common log, which has a base of 10. We're also going to work with natural logs. Natural logs use the symbol ln instead of log. And so if you ever see ln and then the base of ln is missing, the base is e. And didn't we learn about e yesterday? Unfortunately. And you know where it is on your calculator. So that's the value of e. Natural log symbol is ln. All right, so let's look at some properties of log and natural log. Now these are things that you need to know and you need to be aware of, because it's going to help you solve some problems later on. So based upon this is the log form, let's just convert it to its exponential form. Base a to the 0 is equal to 1. We discussed this yesterday. What's anything to the 0 power? 1. So doesn't that mean that that value is 1? All right, so if I needed to solve this, I would actually take this out of log form and put it into its exponential form. And that, let's just say that I didn't know what this was, so it might have been a to the x right there. Log of a to the x equals 0. And if I change it to this, I'll know that x was 1. And that's really what's going to happen to it. All right, what about this one? How are you going to convert it? A to the first, so I'm switching these two, is equal to a. Okay, what about this one? A to the x is equal to a to the x. And I'll show you how these are used in a minute. Now we have natural log. You don't see the base for that natural log, right? What does it assume that that base is? E. So we really have a base of e. So it's what to the what? E to the 0 equals 1. Isn't that true? It doesn't matter that our base is e. Anything to the 0 is 1. And then what about this one? What's the missing base? E. So e to the first is equal to e, which makes sense, right? And then what about this last one? Again, our base is e, so it's just like that log base a of a to the x equals x. This is natural log base e of e to the x equals x. Want to be e to this x is equal to e to the x. We've just manipulated stuff, right? Bless you. So now we're going to use that, and we're going to solve these without a calculator. So these parts will be on your non-calculator portion of your quiz. Okay? So if I had to find the value of log base 2 of 1/8, I'm going to first set this equal to x. I'm missing a variable, right? Well, what I don't know is the value of that. So let's start off with converting it from its log form to its exponential form. What do you get? 2 to the x equals what? 1/8. Because my base here is 2, can I convert this to a base of 2? The 8. Yes or no? Yeah. 2 to the what is 8? Nope. 2 to the what? 2 to the third. So this becomes 2 to the x equals 1 over 2 to the third. Now I want to get this right side, so the base, this 2 to the third is not in the denominator. If I move 2 to the third into the numerator, what do you remember from algebra 1, 2, and 3, 4? Yeah, it becomes 2 to the negative third, right? Anytime you change a base and its exponent in the opposite direction, the exponent changes signs. So this becomes 2 to the negative third, as I can't talk. What's x? Yeah, so x is equal to -3. Now you could have shortened up some of that work, but because these are your notes, we didn't. All right, so let's do the same thing with log base 10 of 1,000. And I said 10 because it's missing, right? And make sure you put equals x. And that's the one thing that you're going to forget to do, is you're going to forget to let it equal x. And then you're going to go, what do I do with this? So what to the what? 10 to the x equals 1,000. Because your base is 10, can I convert that to a base of 10? So I've got 10 to the x is equal to 10 to the, how many 10s will it take to get 1,000? 3. So what does x equal? X equals 3. I find this fun stuff. I could do it all day long. So again, we're going to let this one equal x, right? So what to the what? 27 to the x equals 9. Can you convert both of these to the same exponent? Or let me just say this. Well, yeah, it's going to have to be the same exponent. If I can convert this to 9 to the something, I would, or if I can convert that to 27 to the something, I would, but I can't, right? So this right here becomes what to the what? 27. 23 to the third, and then all of that is raised to the x, right? And then 9 becomes what? 3 squared. And then what is the rule for power to power? What do you do with the exponents? Multiply. So this is really 3 to the 3x equals 3 squared. So now can't I drop my bases and just solve 3x equals 2? And then divide by 3, x is equal to 2/3.
We won't just be able to, I mean, I totally know how to do this, but...
You won't have to show all that work. We're just doing this because it's your notes.
Well, what I'm saying is, we can't just type it on the calculator.
No, not for these ones. These ones will specifically be, your quiz will be split between a calculator portion and a non-calc portion.
Yeah,
Because we want to use our properties to solve these, because what if you didn't have a calculator handy? All right, now this one, we actually have 2 sides and we have a variable, right? Notice that you have a log base 7 here of x, and you have a log base 7 here of 9. If I had this 9, well, isn't x equal to 9? Isn't that logic? Okay. So logic says that x is 9. And my point to you is this: if I can get these to be the same base, whatever we're taking the log of has to be the same number. All right, what about this one? What is this equal, though? make it equal x, even though your x is up there, right? Because I want to show you something. Yes. Whenever your bases are the same, here and here, the value of this is going to be x. And the reason for that is e to the x is equal to e to the x, right? So anytime you have these two right here exactly the same, whatever this number is here, and in this case it's an x, that's your answer. So the value of the natural log of e to the x is just x. This is actually your answer right there. So what if I had natural log of e squared? It would equal 2, and that's the point. What if I had natural log of e to the 1,000,000th? It'd be 1,000,000. What if I had log of 10 squared? I didn't tell you the base was, so what's the base? 10. So if you have log base 10 of 10 squared, what's the value going to be? 2. And that's really what that property is saying. So look at this one over here. You have a natural log and a natural log, 4 and x. What does x have to be?
4.
Yeah. All right, now on the bottom we're going to solve these with a calculator. So notice that these are all, this is log base 10, and it's telling me the 10, it doesn't have to. Notice on this one there's no 10 there, and then this one there's no base, but we understand that it's e, right? So you're just going to take your handy dandy calculator, and you're going to plug in log. So do you see your log button? I'm going to try to zoom out here. Here's your log button, right here. So we're going to hit that log button, and then make sure that you put the 4/5 in parentheses, and close them, and hit enter. Now they didn't tell you how many decimal places to go out to. If I were you, I would go out to, oh, I don't know, 4 or 5. But do pay attention. So this one's negative, isn't it? Did everybody get that? Okay.
You said 4?
4 or 5. So this one was 0, 9, 6, 9. And make sure that you round appropriately. So if I want to round, if I rounded to the 9 here, I'd leave it as a 9, right? Because 1's next door. And if I wanted to round it at the 1, because the 0's next door, I'd have a 1. So either way. 4 or 5. On a test or quiz, I'm going to tell you. If I don't tell you for logs, let's go to 4 or 5. All right, so what's the log of 12.5? $1.09691, right? Oh, that looks very similar, doesn't it? Why? Well, we'll find out later why.
50 divided by 4.
Well, but this decimal 4/5 is 0.8, right? And this one is 12.5. Well, that's not because it's a decimal.
Well, 5 divided by 4 is 1.25. 50 divided by 4 would be 4.
Yep. Yes.
So there's no like number next to the log, it's the same as 10?
Yes. We're assuming that we have a base of 10, and your calculator log button is the base 10 button. When it's a different base, you can't use your calculator. Well, you can't use this button on your calculator. You can't use this button on your calculator if it's like a log base 4. But I'll show you how to use that button on your calculator when we have a change in base. Newer calculators have a change in base formula in it. The older ones don't, but we can still do it. Okay? But that's for another day. All right, so now find your natural log. So you're just going to find your natural log button, which is right below your log button right here. And it's going to use that base of e. So natural log of 2 is 0.6931. Round to the 4, what do you get? A 5. Now this is interesting. You should know the answer to this before you plug it into your calculator. It's a log base e of e squared. But I want you to go ahead and plug it in anyway because I want to prove to you that it does give you 2. So we're going to do natural log, and then we're going to go to second function. Remember, your e is above your division sign, so there's my e, and then we're going to square it. And what did we get? 2. So doesn't that property work?
On the natural log, when you calculate EX,
Yeah.
what's the
that
X?
difference? Is it what
No, I just do.
Yeah, it gives you e to an exponent. So if you wanted to use that button,
It's e to the.
you could do natural log. I never actually used that button. Never thought of it before. But there it just gives you that exponent. So now you can hit squared, and you're still going to get your 2. It's a shortcut, especially if you have to put a bigger number in this. I think it's the same number of keystrokes. All right, so then this one now is different, right? So, change in base formula. Let's see what you have. I want you to go to clear that out, and we're going to write the instructions in our notes in case you miss it. But if I have a different base here, 5. Do you remember in Algebra 3-4 how you learned to do change in base? Divide what?
Log 5 divided by log 12.
Backwards.
Log 12 divided by
Yeah,
log
so it'd be log 12 over log 5. That's how you could do it, but your calculator actually has a change of base formula in there. So you could do log base 12 or log base 10 of 12 over log base 10 of 5, and that would give you the same answer. Or now those of you who have the old black ones, you don't have the change of base formula, but look in your math button. See if I can zoom out here. So look on your math button, and then where are you going to have log stuff? Nope. Nope.
It's under that.
You just have to keep going, right?
You do log
Keep
that
going.
out from that.
Nope.
Yeah.
Nope. Doesn't it say log base?
Yeah, it's a little bit.
Yeah. So find log base. Whose calculator doesn't have log base? It'll be old. Is yours the old one? You should have it. You should have
Sure
it.
enough.
Did you scroll down to number? Oh, I see what you meant by alpha letters. I gotcha. Do you have A? Not everybody's going to be the same. So yours doesn't go past 0? Okay, so you'll have to do the old change of base formula. But for us, look at what my nifty one does. Look at that. I love it. So now all I have to do is put in the 5, right? And then hit my cursor key over and put in the 12. And then it'll do the change in base formula for me. If you don't have it, then you just do it the old-fashioned way, right? So for those of you who want to remember how to do it, you're going to first type in math, right? Then you're going to scroll down until you find your log base. And then you're going to input, in this case we input the 5 and the 12, and our answer turned out to be 1.54390. What happens if I want to, let's go to the 5. 39 what? 6. Okay. So now I want you to find the natural log of -1. Ah, interesting. Natural log of -1. Oh, it yelled at you, right? Here's, you're going to write yourself a note. So error, put error here. Those are ours. You cannot take the natural log or a regular log of 0 or a negative number. So if you were doing the non-calculator portion of the test, and I give you the log of 0 or the log of -1, your answer should be not possible, does not exist. No, don't write error because I don't know that you know what that means. But you can put not possible or does not exist, and that's acceptable. So try to find the log of 0. So if you did the log of 0, it yelled at you again, error domain. See what it's saying? And here's why. Remember what the graph is of, let's look back here. What's the graph of this? Because the log of base A of y equals x, isn't that the exponential form? What's the graph of that look like? Well, flip it over. Look at that. Isn't this a to the x? Okay. Well, this is your graph of log base x, or base a to the x. Because these are inverses of each other. This right here, y is always positive, and x could be any positive or negative value, right? But when we convert it to its log form, when we convert this to its log form, we've actually found the inverse, have we not? Yes or no? That's what you've done. So highlight this right here. The graph of the log and the natural log is the inverse of the exponential function from what we did yesterday. It's actually a reflection over the line y equals x. That's your slant asymptote, right? This is what we graphed yesterday. Its reflection over y equals x is the inverse. So yesterday you could have positive and negative values for x, true? But you always got what kind of value for y? Positive, because the range is greater than 0. But look at this inverse. What's the domain of the inverse? What's the domain? It's only in what parts? It's only in the positive parts of the x-axis, right? So that means that your domain is from 0 to positive infinity. So if I'm plugging in a value for x that's negative or 0, is that even going to have a y value? Over here, if I plug in a negative or a 0 on the x-axis, am I going to get a y value on the inverse function? Remember, this is your log. Isn't this the graph of our log? Didn't we just try to find the log of 0? If I plug in 0 for x, isn't that right here? Is there a y value for 0? No. That's why you're coming up with an error, because this is our graph of that log. Its domain is greater than 0. But notice that the range is from negative infinity to positive infinity. Haven't these reversed themselves from yesterday? In inverse, remember your x's and your y's change. And isn't that what's happened here? Your vertical asymptote is now x equals 0. This is your vertical asymptote. Wasn't it a horizontal asymptote yesterday? So everything has been reversed. You're in your inverse world now. But this is still a continuous function, isn't it? And it's still an increasing function, isn't it? But this time your critical value is 1, 0. Right here. So the critical value has also been the inverse, because the critical value yesterday was 0, 1. So if you flip your x and your y, now your critical value is 1, 0. Fascinating. So now let's look at transformations of the inverse function, which is your log function. So let's go ahead and look at these. So our argument is x minus 1, right? So what is our shift going to be? What's this going to create? Up, down, right, or left? Right, how much? So that hasn't changed, right? So this is going to move to the right, 1. So remember our critical value, because this is a log, our critical value point was right here. If I move it to the right 1, isn't it here now? And don't we have a vertical asymptote here? So this time right and left shifts move that vertical asymptote. So I have to move my vertical asymptote also. my vertical asymptote gets moved to the right 1. So this is x equals 1. And then remember, my general shape is going this direction, it's increasing. So I have to hug the asymptote but go through that critical value. And this is really my dotted line right here, isn't it? Bless you. So it's really going to end up curving. Oops, curving like this. Because we still have the slant asymptote to deal with too. Yes.
So I guess you put 2 for the exit intercept for this. How do you get that?
Because originally my critical value up here was 1, 0, right? So if I shift to the right 1, doesn't that original critical value of 1, 0 shift to the right 1? Yep, just like we did yesterday, right? But now we have a vertical asymptote instead of a horizontal. So this one's outside the argument, isn't it? Natural log, by the way, looks exactly like the log. Well, give or take a little bit, but we're going to assume it's the same. All right, so with a shift of +2 outside the argument, what does that do? Up 2. Does up 2 affect the vertical asymptote? No, nope, because this doesn't change, right?
Well, even though it's the natural log?
Right, even though it's natural log, it's still going to look like this one up here. It has a slightly different curve, but I don't really care about the difference. That's not for this course. So here's our hash marks. Our original, and then this, our asymptote is x equals 0 this time, right? My original critical value was here. If I'm moving it up 2, doesn't it get moved up here? It's still going to hug the y-axis here, but then it's going to curve up here. Don't worry about the movement of the slant asymptote. Technically that gets moved up 2 also, doesn't it? Still has a slope of 1. But I'm not going to make you responsible for that. Don't. No. I won't be that crazy. Although it's really not that hard to do. All right, look at this last one. There's 2 shifts going on here, right? What does this do? Right 2 and up 1. So which one affects the asymptote? The right. So now you're responsible for knowing what the graph looks like for a to the x and what the graph looks like for the log of x. Okay? Because they are different, but they're inverses. So my right 2 means that my asymptote gets moved to the right 2. So it goes through x equals 2. And then my critical value used to be right here, but it's got 2 shifts. It's going to go to the right 2 and then up 1. So here's my new critical value. Oh, we have to show that ordered pair. So isn't this 3, 1? This one over here, by the way, was 1, 2. And this one over here was 2, 0. And so now you just have to hug this bottom, hugs the asymptote x equals 2, and then this one curves away. Right? Not so bad. All right, let's talk about the domains on each one of these. What's the domain here? The asymptote starts that domain. That's the starting point, right? So what's the domain? It starts at 1, right? So but it doesn't include 1. So it's a open parentheses at 1, and doesn't it go to positive infinity? Is this an increasing or a decreasing? It's increasing. And then this one, how does the domain change on this one?
0.
It doesn't change, right? So the domain is 0 to positive infinity. And it's still an increasing function, isn't it? unless there's a reflection. And so the reflection can still occur. But you're less likely to have, well, you might have a couple of, maybe a reflection over the, they could reflect over the vertical asymptote, but most likely your questions aren't going to do that. What's your domain on this one? Yep, so it starts at 2 and goes to positive infinity. And it's still increasing, right? All right, so on these ones down below, I just want you to write the shifts and then the domain. You don't have to graph it, just write the shifts. And then I'll put up here what the answers are. Oh, we better talk about one of them. So look at the first one. You all agree that this is a shift of right to? What's wrong with this one? Why did I stop you and say we better talk about it? Okay, so if I were to switch it, I'd have negative x plus 2, right? That's still not quite right because that should be positive. So then we have the natural log of, I need to factor out a negative from here. And what does that do to what's in the parentheses? X minus 2. So it's still a shift of what? It's still a shift of 2 to the right. But it has a reflection, doesn't it? Does the reflection affect the x value or the y value? Remember, the reflection over the x-axis is going to be at the exponent or at what I would consider the base here. Won't this affect my y value, this negative? Won't it? Yeah, so if it affects my y value, what am I going to reflect it over? Does it affect my y value though? Think about it. Can you take the natural log of a negative, number 1? No. So what's it going to end up doing? If it shifts right to, I'm going to have this vertical asymptote right here of x equals 2, won't I? It's actually going to reflect it across that x equals 2. It's going to reflect it from here over to here. Because you're going to have to choose negative values for x in order to make that negative into a positive. You can't take the natural log of a negative, right? Hold tight. So your other shift is a reflection over the x equals 2. And that's just kind of a weird one. All right, so we'll finish this up briefly tomorrow. But you ought to be able to do your homework, even though we haven't done this word problem. We'll finish this tomorrow and talk about it.